All right, so this is death packet problem number 10. It says, given the probabilities A equals 0.3, B is 0.2, what's the probability of A union B if A and B are mutually exclusive, if they're independent, and if B is a subset of A? So first off, as soon as I see A union B, I'm going to go ahead and write down the addition rule. A union B equals the probability of A plus the probability of B minus the probability of A and B. All right, so A is 0.3, B is 0.2. But if they are mutually exclusive, that means our intersection is 0. So the probability of A union B for the mutually exclusive is just 0.5. All right, so now we're looking at either C or D. All right, then working with independent, if they're independent, then the intersection equals the probability of A times the probability of B. So in this case, probability of A union B equals the probability of A plus the probability of B minus the probability of A and B. So once again, 0.3 plus 0.2 minus 0.3 times 0.2. When we do that, we end up getting 0.44. And that's not a surprise because it had to be 0.44 just because those are only two that I had there. So we're looking at 0.44. And then we have the situation where it talks about subset. Subset means it's completely contained. So if I were drawing a Venn diagram, it would look like something like this. A right here would be 0.3. So this would represent A. Well, B would be completely contained in it. Well, this would make this 0.2. So this area out here is going to be 0.3 minus the 0.2, which is 0.1. But basically the 0.2 of B is contained completely in there. So A union B in this case is just going to be the same as A. So A union B would be exactly the same as A. All right, and I'm going to pause this for just a moment. So this is problem 12 of the death packet, and it says a chess master wins 80% of her games, loses 5%, and draws the rest. If she receives 1 point for a win, a half point for a draw, and no point for a loss, what is true about the sampling distribution of X of the points scored in 2 independent games? Once again, as soon as you do 2 of something or repeat it, I like to go ahead and set up a table. So in this particular case, she can receive 0 points, a half point, or 1 point. So that means I could have in 0, a half, and 1. So I could have 0, 0, 0.5, 0, 1. 0.5, 0, 0.5, 0.5, 0.5, 1. 1, 0, 1, 1, excuse me, 1, and this is a 0.5. That's a 0.5. And this is going to be the 1, 1. All right? Well, this would be getting 0 points, and this happens when you lose both games. Well, there's only one way to get 0 points, but I can get 0 points if I lose both games, which means I got a 0 here and a 0 there, which is going to be 0.5 times 0.05, because I have to get the chance of losing is 5%. When I multiply that out, I end up getting 0.0025. At that point, I actually see my answer already. I already know that it's B, but I'm going to continue on for just a moment. To get a half point, That'd be 0 plus a half and half plus a 0. So that allows me to get it two ways. So to get a half a point, I'm going to lose one and tie the other. I'm going to lose one and tie the other. So losing happens 5% of the time. And let's see, and what was the draw? And she was 1 point for draw. And 15% of the time, they make a draw. All right? So, and I can do that this way, and I can do it this way. A half, and this is going to be 0.50. So this is going to be 0.15 times the 0.05, and I add those up. To have one, to end up getting one win, I can get it three ways. All right, so this will get me 1 point. Each one of these will get me 1 point. These two ways give me 1.5 points, and this one gets me 2 points. And I'm just going to do the last one because it's really quick and know that we can have done all the others. So I could get a 1 and a 1. Well, what's the probability you get 1 point? Well, 0.8, because she wins 80% of the time. And we have to do it twice. And so that gives me 0.64. So 64% of the time, she's going to win 2 games. And so this is going to give me the answer for this one is going to actually end up being B. All right. And once again, the key to this is setting up the table and then assigning the point values. All right, just a second. I'm going to pause this so I can answer questions. So here we go. Number 15 of the death packet. Suppose 4% of the population have a certain disease. A laboratory blood test give a positive reading for 95% who have the disease and for 5% of the people who do not have the disease. If a person tests positive, what's the probability the person has the disease? Okay, whenever I see 3 percentages, or I have a lot of information, I try to organize it. But I see 3 percentages, that's not a guarantee, but it's a good idea. That's usually a pretty reasonable suggestion that we are going to be working with the table. And in this case, I'm going to set this up with the table. All right? So when I go to set this up as a table, my beautiful window, and I always start with the hardest number, 1.0, because that means I actually know something if it's not very much. So I look at these, and I got these 3 numbers, and I need to identify the one that's associated with only one variable. So suppose 4% of the population have a certain disease. Well, this is associated with disease, and it's not associated with a test. This is associated with one variable. So that's the one I'm looking for. So I'm just going to skip ahead and go, you know what? One variable always goes here. 1 minus this gives me 0.96. So we have disease and we have not disease. All right? So take these numbers, I'm going to bring them up. I'm going to write them very small, 0.04, 0.04, 0.96, 0.96. Then it says a laboratory gives a positive reading for 95% who have the disease. So here we're looking for positive and negative readings. And it says positive reading for 95% who have the disease. So positive for those that have the disease. So this is 0.95. 1 minus that is 0.05. I'm going to go ahead and go to the next part. And 5% of people who do not have the disease, it also tests positive. All right? So 5% who do not have the disease. So this is 5%. And then this is going to be 95% because 5% is positive, 95% is negative. And the question is, what is the probability if a person tests positive? All right? So if a person tests positive, so in this case, I'm concerned about the positive group. So I know I have to worry about this part right here. So I'm going to go ahead and finish calculating that out. and use the calculator to do so. So I end up with 0.04 times the 0.95. Oops, I should turn the calculator on. That usually helps, I guess. So 0.04 times the 0.95. This gives me 0.038. This is going to be 0.96 times 0.05. And that ends up being 0.048. If I add those two numbers together, I find out that the probability of being positive is 0.086. And I'm going to need that, and here's why I need that. If a person tests positive, this is just like using the word given. All right? And we know whenever they say given, given goes in the denominator, and we know we're going to have an intersection on top. So given that they're positive, so 0.086, what is the probability the person has the disease? So we're looking at the intersection for disease, which in this case is 0.038. So 0.038 divided by 0.086, and we end up getting 0.4418. So in this case, our answer would be C. All right, so let me pause this real quickly. Okay, so number 18 of the death packet. A computer manufacturer sets up 3 locations to provide technical support for its customers. Logs are kept noting whether or not calls about problems are solved successfully. Data from a sample of 1,000 calls are summarized. Assuming there is no association between location and whether or not a problem is resolved, what is the expected number of successful calls from, in other words, the problem solved from location 1? So I'm just going to go ahead and circle what we're interested in. Problem solved and location 1. Now, key word, assuming there's no association. So pretending like there was no association, what would you expect to happen? If there's no association, we're saying they're independent, which is the probability of A and B equals the probability of A times the probability of B. So the probability would be 450 over 1,000, that's for this, times 700 over 1,000. I'm going to assign this is to A and this is to B. But they didn't ask me for the probability. This would be the probability. They asked me for the expected value. Well, the expected value means I need to multiply by the total. Because if I say, hey, we're going to shoot at the basket, you make 80% of the shots and you shoot 100 times, you're going to go, well, I'm going to make 80 baskets. Or I make 80% of the shots, I shoot 70 times, you're going to go, okay, 70 times 0.8. Well, here's my probability, so I'm multiplying it by the number of times, which in this case is 1,000. So I'm going to mark these out, that drops off, and I end up getting 450 over 700 divided by 1,000, which gives me answer E. All right, so pausing. All right, so we are recording, we're on problem 21 of the death packet. And it says, given that the probability of E equals 0.32, the probability of F is 0.15, and the intersection equals 0.048, which of the following is a correct decision? The events E and F are both independent and mutually exclusive. It's like, okay, so now I know what the question's going to ask me about. It's going to ask me about mutually exclusive, and it's going to ask me about independent. Without doing a whole lot of work here, the very fact that I have this means I have an overlap of 0.048, which means it cannot be mutually exclusive. It cannot be mutually exclusive because mutually exclusive means no overlap. To be mutually exclusive, it'd have to look like this, no overlap. We have an overlap, so it's not mutually exclusive. So now I need a test for independence. Well, the easiest way to test for independence, not the only way, but the easiest way, is the probability of E and F equals the probability of E times the probability of F. So we know that E and F is 0.048, and this is 0.32, and this is 0.15. So when I multiply them, 0.32 times 0.15, I end up getting 0.048. And since 0.048 equals 0.048, they are independent. So in this case, they are independent, but they are not mutually exclusive. Are independent, but not mutually exclusive is letter D. Please remember, for all intents and purposes, you won't be both. The only time that you would be both is if one of the probabilities is 0. So unless you have a probability of 0, you cannot be both mutually exclusive and independent. And if you have an overlap, you will not be mutually exclusive. That's always and forever amen. And also please remember, just because you have an overlap doesn't mean that it's necessarily independent. It's only independent if this times this equals that. All right, so I'm going to pause this for just a moment. Resuming recording. So this is number 28 of the death packet. This is number 28 of the death packet. It says, which of the following is not a probability density function? Well, to be a probability density function, all the probabilities must be between 0 and 1 inclusive. They must be between 0 and 1 inclusive, and they must sum up to one whole. So something that I'm sure we've forgotten about is that probability can be displayed as the area under the curve. Probability can be displayed as the area under the curve. So please remember, f of x from your algebra represents basically the y, the function when y equals 1. And so over the intervals, this would be over the interval 0 to 1. So if I were to draw that, graph, it would look something like this. X is 0, and we go up to, and we're going to go all the way to 1, and we're going to go up to 1. This is my origin at 0, 0. Well, what's the area of that? Well, 1 times 1 is 1. That's a valid probability distribution. So A is a valid probability distribution. When I go to B, B says, you know what? 1, 2, 3, 4, 5. So we're going to go all the way out to 5, but we're only going to go 0.2 in height. So 0.2 times 5 equals 1 whole. So this area is 1, and because the area is 1, that is also a valid probability density function or distribution. Then we have this other one, all right? So we now have, I think I have enough room to get this on the screen. I'll just move this up. There we go. And we're going to count all the way out to 7. So we have 1, 2, 3, 4, 5, 6, 7. And from this part, from 0 to 4, this is 0.1. Well, 0.1 times 4 means this area right here is 0.40. This one goes up to 2. Or 0.2. This height is 0.2. But how many do I have? I have 1, 2, 3. 3 times 0.2 is 0.6. 0.4 plus 0.6 is 1 whole. That also works. Now we're going to get to a trickier one. All right. Not difficult, but it tends to bother people. And by the way, all of these bother people the first time they see it, then later they're like, oh, that's not so bad. All right, so we start off with 0, and we're going to go to 1. That's our x's, 0 to 1. But our y is 2x. Well, that means 2 times, if I have a 0, this is 2 times 0 is 0. And 2 times 1 means I'm going to be all the way up here at 2. So this is the shape, and I have a triangle. Well, base times height divided by 2. Well, my base is 1. My height is 2 divided by 2. 1 times 2 is 2, divided by 2 is 1. So this area is 1. Valid probability. So now we know it has to be this last one. But let's check it out. Let's check it out. One, two, three. So when it's 0, this is 0. 3 times 3, this means this is going to go all the way up to 9 over here. And that's my base. Once again, we have a triangle. Base times height divided by 2. So 3 times 9 divided by 2. And that does not equal 1. Therefore, this is my answer. It's not a valid probability density function. Now, the question is, I'm going to go ahead and answer this there. Will we have one of these on the test? And the answer is no, you won't. But I totally want you all to actually picture probability as an area. And because you're going, when we go back to start talking about the normal curve in the next section, once again, we're looking at the area under the curve. So once again, it's about whether or not these are valid probability density functions is actually a very important concept, but it will not be on this next test. All right, so we're at 35 on the death packet. The Air Force receives 40% of its parachutes from Company 1 and the rest from Company 2. I don't know what they are, and I just see for company. I have no idea if that's what it stands for, but that's what I called it. The probability a parachute will fail to open is 0.0025. That's disconcerting. Or 0.002, whether or not it's from Company 1 or Company 2. So this is basically Company 1's. This is Company 2. If a randomly chosen parachute fails to open, what's the probability that it's from Company 1? All right, so once again, anytime I see 3 numbers, I start going, this is probably a table. And at the very least, I want to start thinking that way and want to start organizing, see if there's a way to organize it. And I know I need to sit there and go, is there one number that's associated with one variable? All right. So when I look at this, I look at that very first number. The Air Force received 40% of its parachutes from Company 1. That has nothing to do with whether or not it opened or not. It's only associated with one variable. This 40% is one variable, so therefore this right here is 0.40. And we go, okay, that makes this Company 1, this makes this Company 2. So 1 minus 0.4 means 0.60. So 40% from Company 1, 40%, 60% from Company 2. And anytime I'm working with the table, I'm bringing up these values just like this. All right. The probability a parachute will fail to open is 0.0025 if it's from Company 1. And I'm going to say F20 fails to open, and I'm just going to call this open. So this is going to be 0.0025, and this is going to be 0.9975 because it's 1 minus that. If it comes from Company 2, there's a 0.002 chance, so this is 0.002, which makes this 0.998. All right. If a randomly chosen parachute fails to open, well, here's my fail to open. So at that point, I know I have to do some work on that. So I'm going to do some calculations. It'll take me just a moment to multiply all that stuff out. So 0.4 times 0.0025 gives me 0.001. And then 0.6 times 0.002 tells me this is 0.0012. Add these two values together. And I get 0.0022. All right. It says if a randomly chosen parachute fails to open. If is another word for given. And anytime I have a given, I know that's going to be in the denominator, and I need an intersection on top of it. And this is sticking to the desk. And my given in this case is 0.0022. What's the probabilities from company 1? So circling there, this is where it crosses. So that's my intersection. So this is my numerator, 0.001. 0.001 divided by the 0.0022 gives me 0.4545. So this gives me an answer choice of D. All right, so looking at 36 on the death packet, there are 8,253 men and 10,327 women at a state university. If 43% of the men and 27% of the women are business majors, what's the expected number of business majors in a random sample of 200? So basically, first off, we need to sit there and go, how many students are there at the university? So I'm going to just add these two values together. 8,253 plus 10,327. So I end up with 18,580. I hope I added this up right because I don't have any work to check it with. So 18,580. Wow, 580. And 43% of men and 27% of the women are business majors. All right. So I need to find out what percent of the students are men and what percent of the students are women. So 8,253, 43% of the men, and hold on for just a moment. I need to pause and think about this for a second. Question made me think, guys. You're hurting, making me hurt this morning. So this is the percentage of men at the university, and of that percentage, 43% are business majors. But then we also have the women. We have 10,327 women out of the 18,580. I sure hope I added all this up right. 27% of them, 27% of that are business majors. So let's calculate those values. And hopefully, and if you're following along in the chat, please let me know if I make a mistake. Oops. 8,253 divided by 18,580 times 0.43. So this number is about 0.190 plus, then we need to do the women, 10,0327 divided by 18,580 times 0.27. So about 15.15. So this, I add these up, and that's about 34%, approximately. All right. 34% of 200. So that's 0.68. And I know I have rounding error because I cut things off, but that's the way you approach the problem. You find the percent of men and then the percent of women. All right. So this gives you the percent of the population that were signing up to be business majors. Number 37, given two events, E and F, such that E is 0.34, F is 0.4, and union is 0.637, are the events mutually exclusive and independent? That's what we're looking for. So real quickly, remember, in order to be mutually exclusive, our overlap has to be no overlap. Well, we don't know if we do or not yet because we haven't done our work. So we have the probability of E union F equals the probability of E plus the probability of F minus the probability of E and F. The union here is 0.637 equals 0.34 plus 0.45 minus our intersection. Well, when I add these two up, .34 plus the 0.45, I end up getting 0.79 minus the intersection. Obviously, in order for this to be true, I have to have an intersection, so they're definitely not mutually exclusive. And 0.79 minus 0.637 is 0.153. So 0.153 equals the intersection. So now I need to check independence. If independent, the probability of E and F equals the probability of E times the probability of F. So 0.153, does it equal 0.34 times 0.45? 0.34 times 0.45, it does. 0.34 does equal 0.153. Therefore, they are independent. Independent, but not mutually exclusive. All right, they're independent, but not mutually exclusive. Which of the following is not a valid discrete probability distribution? To be valid, the probabilities have to be between 0 and 1 inclusive and must sum to 1. Well, 0 and 1, sum to 1. Sum to 1. Sum to 1. I have a negative probability. Oops, slid that up too far. Sorry about that. So going back, 0 to 1 inclusive, 0 and 1 inclusive, and sum to 1. 0 to 1, sum to 1. Between 0 and 1, these also sum to 1. Here I have a negative probability. I cannot have a negative probability. So consequently, that's not a valid probability distribution. Cannot have a negative one. All right, I'm just going to assume that that one's clear. You know what? I'm going to pause just a second. Looking at 39. So this is a difficult one just because of the way the symbols are set up. All right. So following are parts of the probability distribution. So they're telling me these are probability distributions, and since they are, they have to be between 0 and 1 and sum to 1. Well, real quickly, I know that this one has to be 0.3 because the sum of all of these have to sum to one whole. So this is going to be 0.3. So it says X and Y are independent, and that right there tells me the probability of X and Y equals the probability of X times the probability of Y. This right here, X comma 1 and Y comma 2 tells me my intersection is 0.12. When x is 1 and y is 2, my intersection is 0.12. So we don't know what it is when x is 1, but we know that y is 2, so this I don't know. I don't know that value. But when y is 2, the probability is 0.3. So now I have 0.12 equals 0.3x, divide by 0.3, and I end up with getting this equals 0.4. So 0.4 equals x when x is 1. But that's not what they asked me for. They asked me for when x is 4. So we know this has to sum up to one whole. So when I 0.6, 0.9, therefore 1 minus 0.9 means this is 0.10. So my answer here is A. That's a tricky question, and partly it's tricky because of the way it's set up, or recognizing the format. This right here, that symbol represents the intersection. I know the question, will there be one exactly like that on the test? No, there will not be. All right, but I do want you to be able to solve puzzles. So 40 is the question on the death packet that I'm being requested to do, and I'm going to tell you that I was debating as to whether or not to do this because this is going to be tested on the next topic, but I'm still going to show this because you actually know how to do it, or you should be able to puzzle this together. So suppose a manufacturer knows that the 20% of the circuit boards coming off the assembly line have a minor defect. If an inspector keeps inspecting boards until he comes up upon one with a defect, what's the probability have to inspect at most 3 boards? So that means 1, 2, 3. All right. So 1 minus the probability of no defects. 1 minus the probability of no defects. And is that the way I really want to think about that problem? Yeah, that is. So I can have 1 defect, 2 defect, and 3 defects, but I can't have 0. So I want 1 minus the probability of 0, because this is saying having at least 1 defect among the 3. So what happens if I have no defects? Well, 1 minus not a defect, not a defect, and not a defect. So that ends up being letter C. Zoom recording. So this is problem number 43. Is there a home field advantage in professional baseball games? Emotional support from the fans and familiarity with the field seem to make a difference, and the home team has won in approximately 5/9 of World Series games. Assuming probability is constant and games are independent, which is probably not true, but it is, but we're going to act like they are. It's important they tell us that, because they're telling us independent. The home team wins the first game. What's the probability that the home team will win the next 2 games? It really didn't matter whether the home team won the first game or not. The fact of the matter is, the fact of the matter is we're playing 2 games. They're telling us the probabilities are independent. The probability of a win for the home team is 5/9. So the probability of winning the first one is 5/9. The probability of winning the second one is 5/9. They're telling us the probability doesn't change because they're independents. So they're 5/9 squared, right? So that probability A. This is problem number 13 of the death packet. Given a probability of 0.65 that interest rates will jump this year, and a probability of 0.72 that if interest rates jump, the stock market will decline? What's the probability that interest rates will jump and the stock market will decline? All right, so because they've conditioned this, all right, they've given a condition, we have two things that must happen. All right, probability 0.72 that interest rate jumps. And that's a multiplying word. So 0.72 times 0.65, and we can actually multiply those directly, all right, because they've made the adjustment. When they said that if the interest rates jump, then this probability is 0.65. And since they conditioned and said, hey, if this happens, this will happen at this percent, we can go, oh, if this happens, then this happens at this rate. And we can multiply them because they've already do that, okay? All right. Okay, we're looking at problem 17. The probability that a person will show a certain gene trait is 0.8 if the father shows the trait, and 0.606 if the father doesn't. So real quickly, this tells me that they show the trait if the father shows it or if they don't. So this has a condition. They have the trait depending on the father. So both of these have two variables, whether the father has it and whether they show the trait or not, okay? So suppose that children in a certain community come from families and 25% of the time when the father shows a trait, given the child shows a trait, which etc. So we have, in this case, we have three values, which generally tells me I'm looking at a table. Hope I can get this one done quickly and correctly because I'm rushed. And it's not, this one is actually a fairly challenging problem, to be quite truthful with you. 25%. So 0.25. So 25% of the time the father shows the trait, which means 75% of the time they do not. So this is father trait, father not have the trait, child trait, child not have the trait. So I'm going to bring these up, 0.25, 0.25, 0.75, 0.75. The probability is 0.8. So this is 0.8. This makes this 0.2. And 0.06 if the father doesn't have it, the child does. So this is 0.06. This is 0.94. Given that the child shows the trait. So once again, we have a given. And remember, whenever we have a given, that's going to be in the denominator, and we'll have an intersection on top. So intersection over given. So here we go. 0.25 times 0.8 gives me 0.2. 0.75 times 0.06, 0.045. So this is 0.245. That's the probability the child has a trait. That's my given. What's the chance that the father shows the trait? That's 0.2 because that's my intersection. So 0.2 divided by 0.245. And I end up getting about 81.6% or letter D. 81.6% or letter D. Does that make sense on problem 17? Okay, I'm going to stop this recording.